Hi, these are the class notes for section 8.4. To work with this video, you'll need both your notes packet and also your Plainsman periodic table is going to be helpful here. Okay. So section 8.4, I'm going to go through a blank document on the screen that I'm sharing, and I'll type in some of the class notes and I'll discuss some other ones and kind of share things with you as we go through it. So for the beginning part, this is going to cover, the lecture is going to cover polar bonds and polar molecules. So I'm going to start out talking about bonds and how to determine whether or not the bonds are polar. We call that bond polarity. And so that will start with these ideas here of bond polarity. When we refer to bonds, we can talk about them as nonpolar covalent bonds, which means that the electrons are shared equally and there's no greater density of electrons around one of the atoms versus the other. So they're shared equally. Shared meaning covalent, and equally shared meaning there's no polarity to the bond. The other type of bond that I'm referring to here is polar covalent bonds. Sometimes we leave out the covalent because that's understood, and we just call them covalent bonds. In polar covalent bonds, the electrons are not shared equally. In fact, we have a difference in how they're shared. And so I'm going to go ahead and put that as capitals, not shared equally. You can underline it if you already have that written in there. So what does that mean? If we're trying to determine a nonpolar bond where the atoms are sharing the electrons equally between them, and a polar bond where the electrons are not shared equally between atoms. First of all, how do we determine that? So I'm going to change my screen to a different screen that is my version of a Canvas screen and share that, okay? And here I have an example of HCl that I've written with a single bond between the hydrogen and the chlorine 3 different times. And we're going to work with these in different ways. The first one, I'm going to show you the Lewis structure. And that means that I've just put a single bond between the two atoms. And I'm filling in the lone pairs of electrons in order to come up with a value or a structure that shows us the Lewis structure for this. So for the hydrogen, we know that brings 1 electron to the structure because it's in group 1. For chlorine, we know that chlorine will bring 7 electrons to the structure. So we have a total of 1 plus 7 giving us 8. So when we count this up, we've got 2, 4, 6, 8 for our Lewis structure to fill out the octet. And we just need to double check hydrogen with these 2 bonds in, or 2 electrons in this bond has its octet, as does chlorine with the total of 8 between the 3 lone pairs and 1 bonding pair, okay? That's a Lewis structure. The structure that I want to show you now refers to how can we show polarity in a bond. So first of all, we want to look and see what the difference in electronegativity is for hydrogen to chlorine. So turn your periodic table over to the second side, and you should see something that we call an electronegativity table. And we're going to look at the 2 values. For hydrogen, we have a value of 2.2 as its electronegativity. And for chlorine, we look over here and we see a value of 3.2. Now to find the overall electronegativity difference, we take the larger value, 3.2, and subtract 2.2 from that. So we get 1.0 as our electronegativity difference. If we look at the bottom of the table, we can see that that indicates a polar bond, because anything with an electronegativity difference between the 2 atoms that is between 0.5 and 2.0 is an electronegativity difference that indicates a polar bond. So hydrogen to chlorine is a polar bond. Chlorine, as the higher electronegativity, is going to attract the valence electrons that are part of the bond more strongly toward the chlorine and less strongly toward the hydrogen, which means that the hydrogen is going to end up with a partial positive charge. So here's one way we can indicate that. We use on the bond, we use a plus and arrow. Try to do that. So the plus here indicates that the hydrogen end of the molecule has a slight positive charge. And the arrow points toward the end of the bond that has a slight negative. So that's one way to show it, with this plus arrow. Another way to show this partial positive, partial negative duality is to use a sign that we call delta. So I'm going to try to draw one here. The delta sign looks kind of like an S where the end is closed up. So that's a lowercase delta. And then we show that this is a delta partial positive by putting a positive after the delta sign. So what I'm indicating here is that the hydrogen end of this molecule has a partial positive, and that means that the chlorine end of the molecule has a partial negative. So again, my delta sign and then negative. So these are two ways of writing the same thing, indicating that this end of the bond, in this case, has a partial positive charge. This end has a partial negative. So if we had a bunch of HCl's, the partial positive here would attract the partial negative of another molecule. And the partial negative here would attract partial positives from other molecules. That's what we call intermolecular forces of attraction. So those are two ways to draw this, and I'll show you where that goes in your notes. Representing polar bonds two ways. So you should show one with the hydrogen and chlorine with the plus arrow, with the arrow pointing toward the chlorine and the plus on the hydrogen side. And then for the other way to show, you want hydrogen bonded to chlorine with that delta positive near the hydrogen, delta negative near the chlorine. Okay, I don't have a way to draw those in here. That's why I did that on Canvas. Now let's look a little bit more closely at that electronegativity table on your periodic table. So you can see that these atoms are arranged just as they are on the periodic table, and they have a value associated with them, which tells how strongly they will pull on the electrons of a bond when it's with another atom. So right below that table, you can see where it says electronegativity difference, 0 to 0.4. That is going to be the electronegativity difference that gives us a non-polar bond. Then below that, you can see also on the periodic table that when we have an electronegativity difference of 0.5 to 2.0, that is going to be a polar bond. Whereas if we have a metal bonded with a non-metal, that's an ionic bond. So you need to make sure that that's completed on your set of notes. Okay. And that gets us to the sample problems. I just want to talk you through how we would work with these. The first one, 29A, is determine the electronegativity difference for HBr and whether or not that's polar. So we would find hydrogen again on our electronegativity table. It has a value of 2.2. Then we look at bromine, which has a value of 3.0. So 3.0 minus 2.2 is 0.8. We check our table below and find that that gives us a polar bond. So that would be worked with number 29. Okay, so we're using the Plainsman periodic table to get the electronegativity values, find the difference, and then determine whether or not they're polar or non-polar based on the values that we have here, okay, which you also copied into your notes. All right, the next thing we're going to look at now that we've talked about how to determine bond polarity. Remember, polarity of a bond is used by looking at the different atoms that make up or that are on either side of the bond. Now we're going to talk about what that means for a whole molecule. Okay. For a polar molecule, we have a polar molecule if we have that slight negative end and a slight positive end of the whole molecule. Okay. That is kind of the same thing as a dipole. A dipole refers to a molecule that has two poles, partial positive, partial negative. Okay. And that will be a polar molecule. It is possible to have polar bonds in a molecule and have the molecule be nonpolar overall. And that is the example that you read about in the book. For that, if we have CO2, and if you look at your shapes lab, you'll see that CO2 has a central carbon double bonded to two different oxygens which have lone pairs. The carbon to oxygen bond, each of those is polar. And we can check that on our periodic table by looking at carbon and oxygen's values. So oxygen's value for electronegativity is 3.4, whereas carbon's is 2.6, which gives us a difference of 0.8, which is a polar bond. So each of the carbons to oxygens, each of the carbon to oxygen bonds are polar. But because it's a linear molecule and symmetrical with no lone pairs, the polarity is not expressed in the molecule. We don't have one side that's partial negative and one side that's partial positive. And the reason for that is what I have on the screen here. That symmetry kills the polarity of bonds. So a molecule with polar bonds and symmetry will be a nonpolar molecule overall. Because the symmetry will kill the polarity and not allow it to be expressed in the molecule. Okay, that's an important point. If we have polar bonds in a molecule and the molecule is not symmetric, then the molecule overall will be a polar molecule. There's another option, which is not having any polar bonds at all. All the bonds are nonpolar. In that case, it doesn't matter whether the molecule is symmetric or not. We're going to have a nonpolar molecule. Okay, so the only circumstance where we'll get polar molecules is we have to have polar bonds and no symmetry or lack of symmetry. Next up, let's talk about attractions between molecules. These attractions between molecules, in your key it says these are intermolecular attractions, are going to be weaker than either ionic or covalent bonds, and that's true because these are partial charge attractions, so they're not going to be like an ionic bond, and they're certainly not going to be like a covalent bond. The importance of these forces is that they will determine things about a molecule. So whether a molecule, a sample of that compound is a solid, liquid, or gas at room temperature, it will also determine other properties like reactivity and things like that. So that's the importance of these forces, okay? Now let's get to the types of IMFs, okay? On your notes, you would already have determined what's in blue here, okay? And I'm just adding some information in. I actually want to start with dispersion forces, and the reason is that these are the weakest IMFs, or intermolecular forces, when we have small molecules. For our description, we say it's the weakest of all intermolecular attractions caused by the motion of electrons, creating instantaneous dipoles. So what that means is even in a nonpolar molecule, the electron cloud of a molecule will shift, causing a partial negative, very slight partial negative, partial positive, based on the shift in that electron cloud. Here's a very key piece. These are present in all molecules because all molecules have electrons. So even nonpolar molecules are going to have dispersion forces. Sometimes we call these London dispersion forces, named after the person who first described them. And sometimes we abbreviate that as LDFs. So you can call them dispersion forces, London dispersion forces, or London forces, either one of those. Okay? They're present in all molecules, and in small molecules, these are the weakest. The next strongest are up here. Those are dipole interactions called dipole IMFs, sometimes called dipole-dipole IMFs. For dipole interactions, these are the attractive forces when you have a molecule that has a partial positive end and a partial negative end, and they're going to be attracted to the opposite charge, the opposite partial charge in other molecules. So these are going to be similar to, but much weaker than, ionic bonds. And the reason is we have an attraction of opposite charges. Ionic bonds have a true positive and negative, where dipole interactions are just partial positives and negatives. So that is the middle strength for these interactions, intermolecular forces of attraction for small molecules. The strongest type of intermolecular force of attraction that we get in these types of molecules is going to be hydrogen bonds. So hydrogen bonds are the strongest of the IMFs. For the description, these are attractive forces that occur when we have hydrogens as part of a molecule that are attached to a highly electronegative atom, which is also attracted to the lone pair of another highly electronegative atom. In other words, in our molecule, which has to be polar, we can have hydrogen bonding if hydrogen is bonded to nitrogen, oxygen, or fluorine in a molecule. And that sets up for a really strong type of dipole called hydrogen bonding, okay? Which means that the hydrogen has the electrons so kind of stripped off that it's a pretty strong partial positive. Whereas the negative is going to be either the nitrogen that's bonded to the hydrogen, the oxygen bonded to the hydrogen, or the fluorine bonded to the hydrogen, which has a very strong partial positive that's going to attract the very strong partial negative for the nitrogen or the oxygen or the fluorine, that is going to have a strong attraction for the hydrogen end of other molecules that have a strong partial positive. So if I were to rank these in order of attraction, dispersion would be the weakest in strong molecules, dipole would be the next strongest, and hydrogen bond would be the strongest type of the intermolecular force of attraction. All right, that gets us to intermolecular attraction and molecular properties. So we have to first understand about how to find polarity of bonds. Then we have to understand how to find polarity of molecules. Then we need to understand what types of intermolecular forces of attraction occur when we have different types of molecules in place. And now we want to think about what that means for molecular properties. All right, you would already have read this and written the key, which is that the diversity of physical properties among covalent compounds is mainly because of widely varying intermolecular forces of attraction. We've already talked about covalent, simple covalent compounds and ionic compounds, but we haven't talked about network solids yet. Network solids are solids in which all of the atoms are covalently bonded to each other. And a good example for that is diamond. In diamonds, these are made up solely of carbon atoms, and every carbon is bonded to 4 other carbon atoms, which sets up a tetrahedral structure that just repeats itself. In fact, a single diamond is a molecule. It's a network solid molecule. These are going to be actually very, very strong types of molecules, and they're going to have very high melting points. So if we remember back to our description of simple covalent compounds, these are going to have very low melting points if we compare to ionic compounds of the same size. So melting ionic compounds requires great breaking of ionic bonds throughout the solid, giving them very high melting points. However, if these are melting points of simple covalent compounds are relatively low, the melting points for network solids are actually quite high. So for network solids, because these are all covalently bonded, melting network solids requires breaking covalent bonds throughout the solid, making the melting point very high. So in order to have a very high melting point, that is because to melt the covalent bonds must be broken. Whereas for simple covalent compounds, they have relatively low melting points. And the reason is because to melt these, The IMFs, the intermolecular forces of attraction, must be broken or disrupted. But the covalent bonds remained intact, meaning they are not broken. There's a big difference in melting a simple covalent compound as opposed to a covalent network solid. In a covalent network solid, we have to break covalent bonds in order to melt it, whereas melting something like sucrose or water, all we're doing is disrupting the IMFs. We're not breaking any covalent bonds. When we melt ionic compounds, they have pretty high melting points. What we have to do is break the ionic bonds throughout the solid. That gives them very high melting points. In fact, network solids will typically have even higher melting points than the ionic compounds. Okay. All right, that is the class notes for 8.4. And you can go back through and start this as needed and review it. And hopefully we're on the share there. Yes. So take care.